So let us discuss about frequency response of second order system. This is one of the experiment in circuits and controls lab. Actually, this experiment you have to conduct in discrete mode. Since it is IPCC course, I'm going to explain how you can simulate this experiment with the help of multisim tool. So the aim of the experiment is determine the frequency response of a given second order system and evaluate its frequency domain specification. So if you do discrete, you need to take a second order system module, patch cords, error, etc. Since we are doing in multisim, so you can get virtual components only. So these are the formulas used. So standard second order function is given by g of s is equal to omega n square divided by s square plus 2 zeta omega n s plus omega n square, where omega n is the undamped natural frequency. Omega n is equal to 1 over root of LC radians per second. Damping ratio zeta is given by R by 2 into root of C by L. Damped frequency omega d is equal to omega n root of 1 minus zeta square radians per second. And gain in decibel is equal to 20 log of V naught by Vi. To find the phase angle, this is a Lysage's pattern. So this is the response of output waveform versus input. Okay. So sinusoidal waveform, if you take, that is a, with respect to time, its amplitude is displaying. Now it is actually voltage versus voltage, output voltage versus input voltage. So you are going to get like this patterns. So this is used to find the phase shift between input and output waveforms. So the formula is phi is equal to sine inverse of y1 by y2, where y1 is, you can take peak to peak, or you can take only from 0 where it is actually intersecting the y-axis. This width you can take, half of this also you can take, or you can take peak to peak also. You can take only this much, and maximum this, where it is intersecting at y, and from 0 axis maximum y. So that will give you the phase angle between input and output. Okay, now the circuit you have to rig up is, you have to take one decade resistance box, inductance box, and capacitance box, one function generator and CRO. So in the multisim tool, we have to pick one resistor, inductance and capacitor and oscilloscope and AC power source or AC voltage source, anything you can take, and we can simulate. So virtually you can conduct this one. First we have to keep input voltage constant 2 volts, and here we have to choose different values of R. That is, for R is equal to, I'll show you, for different values of R you have to execute. That is, R is equal to 2 zeta. This is zeta, not delta. This is zeta only, by mistake. Delta is there. This is 2 zeta divided by root of C by L. For 100 ampere, zeta is actually less than 1. You can take 0.5 or 0.3. Calculate what is the value of R1. And for critically damped, zeta is 1. Find out what is the value of that R2. For over damped, zeta is greater than 1. So you can take 2 or 1.5, anything. Okay. So we'll execute for all these different values of R, and we can find, you can see the frequency response. So I am going to rig up this circuit R, LC. R I will take for 3 different cases: under damped, critically damped, and over damped. So this is the value of L and C, you can assume. Find the value of R for under damped, over damped, and critically damped. Okay, now actually in the descript, we are going to keep input voltage towards constant. R value for under damped, you can select 1.5 kilo ohm for given value of L and C. We'll show the calculation. After that, frequency you have to set for 50 hertz, then 60, 70 hertz, 80 hertz, 90 hertz, 100 hertz. Note down the output voltage. Find out the gain in decibel. That is 20 log of V naught by Vi. And to find the phase angle, You have to find out intersection from the Lysage's pattern. You have to find out what is y1, what is y2, and phase angle is sine inverse of y1 by y2. Similarly, same thing you have to repeat for overdamped for different value of r. Again for overdamped. So this is a model response. This is the frequency response, that is gain versus frequency, and this is the phase angle versus frequency. So let us simulate. I will take this. Say I will tell you the value. What is the value of R and L? So let design is started with L is equal to 2 Henry and C is equal to 0.32. So we have to find out what is the value of R. For underdamped, zeta is 0.3. Delta and zeta both are same. Okay, here. So I will find out what is the value of R1 for first case. What is the value of R for underdamped? So I have to find out 2 into zeta divided by root of C by L. So 2 into zeta value is 0.3. Okay, it is this much divided by root of C is 2, L is, sorry, C is 0.32 micro. So to write 0.32 micro. So you're going to get 1500, it is 1.5 kilo ohm resistor you have to put for the first case. So let me take open the multisim tool. So first you have to place the component, go to place component. I want to select resistance R. So it will be there in the basic groups. So select R. Then you can directly select 1.5 kilo ohm, or you can select 1 kilo and double click and change the value to. So R is placed. Then in capacitor you take, capacitor is 0.32 micro. Okay, 0.32 micro. Then one inductor. This is double click and change the value to 2 Henry. And this is 0.33 is almost same. So if you want, you can change it to 0.32 only, exact value. So after that, we want to place one oscilloscope, and we want to give input from the signal source. So place component. It is available in the source. You can select AC power or AC voltage source. So if you want RMS value, go to power source AC power, or if you want to know peak to peak voltage, go to signal voltage source. Here signal AC voltage, click here. So it will show peak now. If you select power AC source, AC power, it will show RMS value. So now this you keep 2 volts peak to peak. So it's a 2 volts peak to peak 1 kilowatt signal, and make the connection. This if you want you can change. Anyway, we are finding frequency response for all the frequency values. Okay, you can change this one to 500 or 1 kilo or anything is okay. So after that we need to find AC response. So we will connect one probe here. Okay, that probe is available here. Voltage probe. This is a voltage probe. So in multisim 11 and all, in the down right side corner down, here somewhere we will get probes, IC voltage marker, IC voltage marker you have to place here. This is multisim version 14.2. So in the 14 higher version, it is available here only, markers. Okay. Okay, now this is output, and we need to place one ground also. So ground is available, place component. The sources, ground is there. You can click here. So after that, okay, now first I will show the frequency response, where we should get a model graph like this. So we connected R, L, C. R value is 1.5K, that is for over underdamped. We kept the input voltage 2 volts peak to peak. We connected oscilloscope or CRO. Okay. So now we have to plot frequency response. So starting frequency, you can start from 50 Hertz up to 1 megahertz. For each frequency, output is going to vary. So that output voltage you have to calculate. After that, normal gain is output voltage divided by input. We kept the input voltage 2 volts constant, peak to peak. That you have to, and you can express gain in decibel as 20 log of V naught by Vi. To find the phase angle, okay, we have to press XY button in the oscilloscope, where it will take channel A versus channel B. Okay, output by input, output voltage by voltage. Okay, it will give you the Lysage's pattern. From the Lysage's pattern, you have to find out what is the value of Y1, that is from this horizon. You can take this, or you can take half of this. Okay, in both the cases, half of you will take, that will be similar to taking peak to peak of this portion where y-axis is intersecting with that curve, and maximum in the y direction. Y2 is maximum from here to here. Y1 is actually it is touching y-axis, no, that part. So sine inverse of y1 by y2. That is the phase angle between the two waveforms, input and output. So now I will go to plot how to plot that frequency response. In discrete component, you have to make the table and all. In the simulation, we have simulation, then go to analysis and simulation, then go to AC sweep. In the AC sweep, you have to specify what is the starting frequency and what is the stop frequency. I'm going to take the reading from here. I'm taking the reading from, if you are doing discrete component, from the signal generator, set the frequency to 50 Hertz, note down the output voltage, 60 Hertz, note down the voltage, 70, 80, 90, 100, after 100, 200, 300, 400, go up to 1K, after 1K, 2K, 3K, 4K, then 10K, 20K, 30K, then 100K, 200K, 300K, like that. Last frequency, you can select 1 megahertz. Okay, now in the simulation also, you have to give starting frequency is 50 Hertz, end frequency is 1 megahertz, and sweep type is decade type, and then vertical scale is vertical scale is let us check not logarithmic, linear. Let us see. Disable. Let us check it out. This one, okay. And this is the frequency. Starting frequency 50 hertz. End frequency is 1 megahertz. Sweep is decade type. Vertical is decibel. Okay. If it is not coming, let us change it to logarithm later. Okay. Next, we have to select important, very, very important. Go to output tab. In the output tab, if you place probe, we already placed probe, no? If you place probe, automatically that is available here. If you mark a probe, it automatically that will come here. If you don't place probe, then you have to take voltage across capacitor. So V of capacitor, it is actually showing I of capacitor 1, I current across R1, current across V1, power across C1, like that, no? So better you connect one probe, automatically that probe is coming here. So output variable is voltage across probe. Okay. And frequencies are this. I'm varying the frequency when we are measuring the output voltage across probe 1. So automatically it is going to plot. Now run. Okay, I'm clicking run now. See, it is coming like this. It is actually almost similar to your model graph. See here, actually the frequency, starting frequency is 1 hertz, 100 hertz is there. So that's why here it's showing. So let us take from 0 hertz only. Okay. So if you want to change that range now, then you have to double click on the AC sweep. Go to once again simulate, analysis and simulation, AC sweep. You can give this as 10 hertz. From 10 hertz only we are plotting. So you are going to get like this. See what happens if I click this is phase magnitude response. See, up to 100 hertz, up to 100 hertz here, what is the frequency? So this frequency here somewhere, somewhere here. Okay, this is 100. See, 100 hertz, 10 hertz, 20 hertz, 30 hertz, 40, 50, 60, 70, 80, 90, 100. So this is 100 plus 100, 200. So it is not exactly 200. I think little bit less. 190 something it is coming here. You can have, oops, let us see. So x-axis you can say 190, 190 somewhere here, 196 or 198 it's coming here. Okay. Delta x-axis from this is one probe is there. Delta x means from this to this difference is 198. So let us calculate what is the uh, natural frequency formula. Omega n is 1 over root of LC radians per second. Okay, now we'll find out what is the frequency it's coming. So it is omega n is 1 over root of LC. Fn is 1 by 2 pi. Omega n means 2 pi Fn. Okay. So Fn is 1 by 2 pi root of LC. So let us find out what is the value of that. 1 over 2 pi root of 2 into pi into root of LC. L is 2 Henry. C is 0.32 micro. Okay. So this answer is say 198.9 hertz. So omega n is 1 over root of LC radians per second. Frequency omega n is 2 pi Fn, where Fn is 1 over 2 pi root of LC. It is hertz, 198 hertz. It is should come. So here in the simulation, we are getting 188.9. Okay. Somewhere here you are getting omega n. So after that, the frequency, if you increase the frequency of that, the gain is actually start reducing. Finally, it will reach 0, 1 megahertz. And similarly, you can calculate phase shift between here you can get phase shift as here phase shift. This is for 10 hertz. Phase shift is 20, some 10 degrees somewhere here. At the 200 hertz, phase shift is around 100 hertz something is coming, 100 or 80. Here minus 160, minus 200, minus 200 like that it is coming. Okay, this is the phase angle versus frequency. So at 100 hertz, phase angle is around 20, minus 20. So you can see y-axis is phase angle in degrees, x-axis is frequency. So this is for underdamped. Okay. So we have zeta is equal to 0.3. For this is coming like this. So now, see this is, you can change background white or black. Okay. So now this is over. This is for zeta, R value is equal to 1.5K. Similarly, you can calculate for, okay, I will show how to find this phase shift. To find the phase shift, you have to go to this and you should not go for AC sweep now. You have to go to analysis and go to interactive simulation only to find the phase shift. So run this and double click on this. You can see both input and output. Channel A, it is connected to what output? Okay. Channel B also you have to connect. So stop the simulation. Second probe, you connect to input. Channel B, you connect to input side. Okay. One channel ground is enough. See both the negative of channel A and channel B are connected to ground. So now run this. Say remember to find the phase shift, it should be interactive. To find the frequency response, it should be AC sweep. Okay. So to find the phase shift, it should be interactive. Then double click on this. You can see both input as well as output. If you want, you can change the output output value to different color. Segment color as some green color you can give. Okay. Input you can give some red color, some blue color. Okay. Now I'm running this. Double click. So input output both you can increase the time axis. Okay. Single. Now I want to find phase. See, you can see the phase shift, the phase difference between this and this. Both are not starting at same point. So to find the phase shift, so it is output versus input. Output is channel A, right? Output is connected to channel. Input is connected to channel B. Output is connected to channel A. So I want to find out output versus input. That is voltage versus voltage. So here channel A, channel B is there. So you type A by B. Here this is A by B. Both phase difference between you can select input versus output. This is output versus input. A by B means output versus input. Okay, you're getting now. Now phase shift is given by sine inverse of y1. This how much? This is 0.2, zero point 0.4. Okay, x-axis above 0, zero point 0.4 is there. Below also 0.4 is there. If you want to take peak to peak, okay, zero point 0.4 plus zero point 0.4 is 0.8. 0.8, and this is 1.8. Okay, 1.8 and 1.8. So sine inverse of phase shift is sine inverse of, okay, this is 0.4, 0.4, it is 0.8 divided by, this is 1.8 and 1.8. So 1.8, 1.8 is 3.6. So it is 12 degree. Okay, it is coming 12 degrees. So similarly, if you change the frequency here, this phase shift is coming for 500 hertz. Okay, next you change this one to 600 hertz, 700 hertz, 800 hertz, 1K, 2K, 3K, like that. Each time you have to execute to interactive simulation and you have to get the Lysage's pattern and you have to plot graph. So the model graph is, this is the See, this is for magnitude plot. Okay, each time you have to vary the frequency, note down the output voltage. For phase shift, you have to note down phase angle. So here only it is there table y1, y2 for each frequency. You have to note down y1, y2 and note down phase angle. So this is the first response is what we are getting. See to see the frequency response, to see the phase response, it should be interactive. To see the magnitude response, it should be simulate, should be AC analysis. So AC sweep starting hertz is 10 hertz to 1 megahertz. Output is voltage across probe 1. So run this. Okay, this is coming. So next, so it is matching with theoretical value also. Fn is equal to 198, and we are getting around 12 hertz at around 500. We are getting 12 hertz. But, this is actually a degrees. So you have to calculate theoretical value in degrees only if you want to match it. So now I will change the value for another value of R for critically damped. So critically damped zeta value I have to take it as 1. Okay, zeta is 2 into 1 divided by tau tau v2. One is 2 divided by tau 0.32 5k. So R value R2 is 5k. So change this one to 5 kilo instead of 1.5. Change this one to 5 kilo and run it. This is for critically damped. Note on the changes here. And similarly, for third case, this will be 10k. So we are adding, this is 2 times of this. So this value multiplied by 2, 5000 into 2 is 10k. So we have to change this one to 10 kilo ohm. So note down this. This is for critically damped. Change this one to 10 kilo ohm. So this is the frequency response of overdamped for zeta is equal to greater than 1. Okay.